Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
Thanks for tuning in. This is part of Dr. Jim's video series, Random Thoughts on Structures. LinPro is a free, lightweight, graphical, easy-to-use computer program that Dr. Jim uses to analyze two-dimensional beams and frames. In this video, he attempts to reverse engineer the default LinPro element. Dr. Jim recommends downloading a copy of LinPro for Windows from the web. Alternatively, get yourself over to Dr. Jim's website at drjimsstructures.com and download a copy from there. There's a link to Dr. Jim's website in the description. Example 1.4 from Dr. Jim's video series on bending and beams provides an easy-paced introduction to LinPro by building a computer model of this two-span, simply supported beam. And here's LinPro with the model loaded. You might want to watch that video before finishing this one. If so, click the link on the screen. The model is complete, and clicking the green arrow runs a static analysis. It's super quick and the display changes to show the deflected shape. Clicking the M button shows the bending moment diagram. Clicking the T button shows the shear force diagram. Clicking the N button shows the axial force diagram. And clicking the R button shows the reactions. These all agree with our hand calculations from example 1 in Dr. Jim's Bending and Beams video series. There's a link to the series on the screen. The white button to the left of the green analysis arrow shows the structural layout. And the button to the right of the green analysis arrow gives access to tabular results. And the delta button shows the deflections. Be aware that the numerical values of the deflections are not meaningful, because the model was built using LinPro's default member properties. To obtain meaningful deflections would require knowing and using the actual material and geometric properties of the beam. So what are the LinPro default properties? Good engineers are curious people, so let's go explore. Exploration and discovery is a great way to learn. Clicking the Cross-Sections button opens the Member Properties dialog box. Notice the Cross-Sections dialog box is used to define material as well as geometric properties. Now look at the numbers. Do you recognize anything meaningful? To be honest, the numbers look a little odd. They are very round. If you thought that, then award yourself a bonus point. Geometric properties are often tabulated in centimetres, and changing the model units to kilonewtons and centimetres gives us more usable numbers. We see that in centimetres, the modulus of elasticity is 20,000 kilonewtons per centimetre squared, the cross-sectional area is 100 square centimetres, and the moment of inertia is 10,000 centimetres to the fourth. Dr. Jim recommends that you use the term second moment of area rather than moment of inertia, because inertia has nothing to do with what's going on here. But then again, Dr. Jim is a little bit old school. If you recognise the modulus of elasticity as being that of steel, then well done. Values of 20,500 and 20,700 kilonewtons per centimetre squared are also often used, and usually they're stated as 205 and 207 kilonewtons per millimetre squared. Dr. Jim also dimly remembers the coefficient of thermal expansion for steel to be 11 times 10 to the minus 6, and that pretty well confirms that the default LinPro elements are made from steel. To proceed, let's assume the default members are solid squares of steel. Unlikely, I know, but simple. The second moment of area of a rectangle is BD cubed upon 12, so a 10 by 10 centimetre square cross section would have a second moment of area of 833.3 centimetres to the fourth, which is exactly 12 times smaller than the LinPro value. That's curious. Note the cross-section axes are labelled YY and ZZ because traditionally the XX axis runs along the length of the member, that is, into the screen. Our square cross-section has the correct area, but its second moment of area is far too small. Continuing to guess wildly, assume that the default element is a solid rectangle of steel, again unlikely, B centimetres wide and D centimetres deep. This involves two unknowns, B and D, but we know two geometric properties, the area and the second moment of area, so we can solve this. Starting with the area, A equals B times D equals 100. Hence B equals 100 divided by D. Call that equation 1. Next, the second moment of area. IYY for a rectangle equals BD cubed upon 12 equals 10,000. Hence B equals 120,000 divided by D cubed, equation 2. Equation 1 equals equation 2, hence 100 divided by D equals 120,000 divided by D cubed. Multiplying both sides of that equation by D cubed upon 100 yields D squared equals 1200. Hence D equals 34.64 centimetres and B equals 2.887 centimetres. What do you think? Well, a section of these dimensions makes little engineering sense because it's far too slender to be of practical use. So what's next? Any thoughts? At this point, Dr. Jim stopped to have a well-earned cup of coffee, and he got to thinking that a sheet of steel 1 centimetre thick and 100 centimetres high would have the correct cross-sectional area. His next thought was that sheet of steel could be folded to make a 25 centimetre square hollow section. Genius or what? Of course, the section does not have to be a square. For example, it could be a 20 by 30 centimetre rectangle. But a square is simple, and now is a good time to introduce section tables. Around the world, steel companies make a range of hot rolled steel sections such as universal beams, universal columns, T-sections, circular hollow sections, rectangular hollow sections, etc. The properties of these member types are tabulated in what are known as section tables. It makes engineering sense to use tabulated values rather than guessing shapes and calculating section properties. Excited by this thought, Dr. Jim let his coffee go cold while he searched the web for section properties of square hollow sections. Clicking the first result opened an online section table for square hollow sections, published by Tata Steel. There's a copy of the link in the description. The third column of the table shows cross-sectional areas. We will scan down that column looking for cross-sectional areas close to 100 square centimetres while simultaneously checking the second moments of area in column 5. Here goes. 180 section, IYY too small. 200 section, IYY still too small. 220 section, too small. 250 section, close. 260 section, almost exact. 300 section, much too big. The 260 by 260 by 10mm section has an area of 98.9 centimeters squared and a second moment of area of 10,200 centimeters to the fourth. So we now know that the default LinPro member approximates to a 260mm square hollow section with a 10mm wall. You might like to see if you can find a better match using a different section table, say universal beams, and there's a link to UB section tables in the description if you want to try that. And if you would like an annotated printable copy of this solution, head over to Dr. Jim's website. There's a link in the description. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. So, bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.